Now let's consider the energy states for a hydrogen atom using all four quantum numbers. So the lowest energy level is n equal 1. And so if n equal 1, the only value L can have is 0. The only value m sub L can have is 0. M sub S can be plus or minus 1/2. So now, what if n equals 2? Then L can equal to 0 or 1. M sub L can equal 0 if L is equal to 0, or if L is equal to 1, M sub L can be equal to -1, 0, or +1. And M sub S can still equal just plus or minus 1/2. Now, if n equals 3, L can equal 0 or 1 or 2. M sub L can equal 0 for L equals 0, or -1, 0, and 1 for L equal 1, or -2, -1, 0, -1, or +1, +2 for L equal 2. M sub S is always equal to plus or minus 1/2. So what this shows is that, say for the n equal 3 level, then L can have 3 separate values. M sub L can have 1, 3, or 5 separate values, depending on the L value. So there are a multitude of energy states available for each n value greater than 1. So let's look at n equal 2. L can equal 0 or 1. M sub L can be 0 or -1, 0, and 1. What does this mean? So this means the energy for the n equal 2 state is this value. Oops, that's not RD squared 2. So minus R sub H over 4. So an electron with this energy can have different values for the other quantum numbers. So we can have n equal 2, L equal 0, or M sub L equal 0. That's one energy state. We can have n equal 2, L equal 1, or M sub L equal -1. That's the second energy state. N equal 2, L equal 1, M sub L equal 0. That's a third energy state. N equal 2, L equal 1, M sub L equal 1. That's a fourth energy state. So there are 4 total energy states for the n equal 2 level. They are all the same energy because the energy is only given by the n value, the principal quantum number. They're all the same, they equal 2. But we can have various combinations of L and M sub L, depending on the criterion for their relationship. So, we have 4 total states in the second energy level, depending on these quantum numbers. So we have a systematic way of writing these. Instead of writing just numbers, what we'll do is write a number, and for the n quantum number, For the L quantum number, we'll write a letter. And then for the M sub L quantum number, we'll write it as a number, but we'll have a subscript. So that way we don't get confused if n equals 2-digit number. Say if n equals 10, is that n equal 1, L equals 0, or n equal 10? So if we let L be a letter, it's a much better way of writing the combination. So historically, they didn't do it alphabetically, but historically L has been given the following letter designations. If L is 0, we give it an S letter. If L is 1, we give it a P letter. If L is 2, we give it a D letter. If L is 3, we give it an F letter. And L equals 4, then we just start going alphabetically from F. So L equals 4 is G, L equals 5 is H, and so forth. Now, why didn't we start with A, B, C, D? Well, historically, before we understood completely the hydrogen atom, scientists were doing experiments, and they were using light to look at the transitions between energy states of the hydrogen atom, and they gave names to the absorption and emission frequencies of their experiments. And so these names were just based on the way they looked experimentally. So S for strong, principal for P, diffuse for D, fundamental for F. And then they stopped using names, just went alphabetically. So now if N equal 1, L equals 0, M sub L equals 0, we use the following symbol. 1 for N. If L is 0, that's given the S symbol, and M sub L is 0, so we write it as a subscript. If N equals 2, L equals 1, and M sub L equals, say, 1, we would write 2 for N. L equals 1 is given the P letter, and the M sub L will be a subscript, so we'd write a subscript 1. This is a way we can write in shorthand notation the quantum numbers, the 3 quantum numbers, N, L, M sub L, for the hydrogen atom. So we have one more example. So we have that combination. We would write 3 for N. L equals 2 is given the D symbol. The M sub L is a subscript, so it would be a 3D minus 1 energy state.